All right, let's dive into a problem that trips a lot of people up, especially if you're prepping for something like the GATE DA exam, likelihood sampling. You see a problem like this with all its tables and variables, and it can feel a little intense. But here's the secret. It's really just a clever way to estimate probabilities by looking at different scenarios. We're going to break this whole thing down into 5 super simple, logical steps. By the end, it's all going to click, I promise. So, here's our game plan. We'll start by just taking the problem apart to see what we're working with. Then, we'll figure out what we're asking versus what we already know. After that, we get to the fun part, calculating some weights. We'll pop those into a simple formula and boom, we'll get our final answer. Let's get started. First up, Section 1, deconstructing the problem. Before you can solve any puzzle, you have to lay out all the pieces on the table and see what you've got. That's exactly what we're doing here.
Okay, this is our mission. This is the question we need to answer. All this notation really means is, what are the chances that B is true if we already know for a fact that A is false and C is false? Let's see what clues the problem gives us to figure this out. First thing we have is this Bayesian network. You can think of this as a cause and effect map, or kind of like a set of dominoes. The arrow from A to B means A affects B, and then B goes on to affect both C and D. A is the starting point here. Nothing else points to it.
Next, we get these tables. Don't let them intimidate you. These are just our cheat sheets. They're called conditional probability tables, or CPTs, and they give us all the numbers we're going to need, like the probability of B being true if A is false, and so on.
And finally, the problem gives us these 4 pre-made scenarios or samples. This is our raw data. Our job is to take this data and use this likelihood sampling method to figure out how important or how weighty each of these samples is for answering our specific question. Okay, now for Section 2, query versus evidence. I really want you to focus here because this is, without a doubt, the most important step. If you get this part right, the rest of the problem is practically going to solve itself. The definitions are actually super simple. The query variable, that's just the thing we're curious about, the thing we're trying to find the probability for. And the evidence variables, that's the stuff we're told is already true, the facts of the case, if you will. So let's apply that to our question. P of B by minus A minus C. What are we asking about? We're asking about B. So B is our query. And what information are we given? We're told that we have minus A and minus C. That's our evidence. So A and C are our evidence variables. Getting this distinction right is the key that unlocks this whole method. All right, Section 3. This is where we get our hands dirty and get to the heart of the method, calculating sample weights. We're going to go through each sample one at a time and give it a score, or a weight. And the whole trick is that this weight is based only on our evidence. Let's kick things off with sample 1, negative A, negative B, negative C, positive D. Now remember, when we calculate the weight, we're only going to pay attention to the parts that match our evidence, which, if you recall, are the variables A and C. Okay, let's walk through this together. We look at A first. Is it evidence? Yes, the sample has negative A, so we look up P of negative A in our cheat sheet, and that's 4/5. Next up is B. Is B evidence? Nope. So for any variable that's not evidence, we just assigned it a weight of 1. Now why 1? Because we're not reevaluating the probability of the whole sample, we're just adjusting its importance based on our given evidence. Okay, on to C. Is it evidence? Yes, it is. The sample says negative C, and its parent, B, is negative. So we look up the probability of negative C given negative B, which is 3/5. And finally, D. Not evidence, so it also gets a weight of 1.
Now, we just multiply those numbers together. We've got 4/5 from A and 3/5 from C. Multiply those, and you get 12/25, which is 0.48. That's the final weight for our first sample. See? Not so bad.
1 down, 3 to go. Let's do the exact same thing now for sample 2, which is A plus B minus C plus D. Okay, the logic is the same, but watch for the one small change here. For A, it's still evidence. It's negative A, so we use that same 4/5. B is still not evidence, so it gets a weight of 1. But look at C. It's still evidence, and it's negative C, but its parent in this sample is plus B. That changes things. We need to look up the probability of negative C given plus B, which from our table is 2/5. And D, of course, isn't evidence, so it's a 1. So we multiply 4/5 by 2/5, which gives us 8 divided by 25. That comes out to a final weight of 0.32 for sample 2. And here they are, all 4 sample weights in one place. You can probably see the pattern here, right? Sample 3 looks exactly like sample 1 in terms of the evidence variables. It has negative b as the parent of c, so it gets the same weight, 0.48. And sample 4 is just like sample 2 with plus b, so it also gets a weight of 0.32.
We have officially done the heavy lifting. We have all our weights. Now it's time to move to section 4, the estimation formula. This is where we take all our hard work and combine it to get the final result. And the formula itself is, well, it's actually beautiful in its simplicity. To get our answer, we just add up the weights of all the samples that match what we're looking for, and then we divide that by the sum of the weights of all the samples. That's it. We are on the home stretch, section 5, deriving the final answer. Let's just plug in the numbers we worked so hard to calculate and see what falls out.
Okay, first things first, let's figure out the top part of our fraction. Our query, remember, was about the probability of b being positive, or plus b. So let's look at our samples. Which ones actually have a plus b in them? Ah, there they are, sample 2 and sample 4. And the weights for both of those were 0.32. Now we just build our formula. On the top, we sum the weights that match our query, so that's 0.32 plus 0.32. On the bottom, we just sum up the weights of all 4 of our samples. That gives us our final fraction, 0.64 divided by 1.60.
And when you run that calculation, you get our final answer, 0.4. The estimated probability of b being true, given that a and c are false, is 0.4. And just like that, we've done it. We've cracked it.
So we solved our problem, which is awesome. But now that you have the method down, here's a little something to chew on. Using the exact same 4 samples and the exact same weights we just calculated, what other probabilities could you estimate? Something to think about. Thanks for joining me on this one.